Hi everyone, this is Becky, and in this video we are going to take a closer look at stoichiometry involving limiting reagents and percent yield. So the goals of this video are for you to be able to understand the idea of limiting reactants and to be able to identify which reagent in a reaction is limiting, and then to be able to solve the stoichiometry problems involving a limiting reagent, and then to be able to work with percent yields and figuring out actual and theoretical. So a couple of things just right off the bat. I'm going to use two words interchangeably, reactant and reagent. Those two mean the same thing. So if I say limiting reagent, it means the same thing as limiting reactant, and I'm going to use both of those two terms interchangeably. Okay, so to give us an idea of what it means to have a limiting reagent, let's think about making sandwiches. Let's say that I'm going to make sandwiches. And I'm making cheese sandwiches, and I'm making the world's worst cheese sandwiches because I know that I need 2 slices of bread plus 1 slice of cheese makes 1 sandwich. Okay, and so I look at my cabinet and I figure out that I have 5 pieces of cheese, but I only have 6 pieces of bread. How many sandwiches can I make? Well, okay, so right off the bat, you probably just said, without doing anything in your head, 3 sandwiches. Well, how did you figure that out? What you probably did was took something like, all right, I have 6 pieces of bread. And I know that if I use all of my 6 pieces of bread, I can make 1 sandwich for every 2 pieces of bread, which means that using all of my bread, I can make 3 sandwiches. If I use all of my cheese, I know that I have 5 pieces of cheese. And I know that for every 1 sandwich, I need 1 cheese. And that tells me that I can make 5 sandwiches if I use all of my cheese. Well, okay, so clearly 3 sandwiches is less than 5 sandwiches. So if I use all of my bread, I can make 3. So I'm going to have some of the cheese left over. I'm going to use some of it, but I'm going to have some of it in excess. The bread in this case is my limiting reagent, because it runs out first. So it determines how many sandwiches I can make. The cheese is my excess reagent, because when the reaction is complete, I'm going to have some of this left over. I'm going to use 3 pieces of cheese, but I'm still going to have 2 remaining, making it my excess reagent. So when we think about this in terms of chemistry, if I were to define a limiting reagent, it's going to be the one that determines how much product I can make. It's completely consumed. Whereas the excess reagent is going to be the one that's left over. So when the reaction is complete, I will have used all of my limiting reagent and turned that into product. So I'll have products plus some leftover excess reagent remaining in my reaction container. So to take a look at what this means, let's look at example problem number that's on page 27 in your packet. So on page 27 in your packet, there's a problem that says that you're reacting together 2.5 moles of copper and 5.5 moles of silver nitrate, and it's asking you to find the limiting reagent. Okay, so let's take a look. I'm going to divide my screen in half because I'm going to do this 2 times just to show you that it doesn't matter which way I do it. So the easiest way to do this is going to be to convert both of these into moles of product and see which one is bigger or which one is smaller. The smallest one is going to be your limiting reagent. So I'm going to do this using, first by converting them into moles of silver, and then second by converting them into moles of copper nitrate, just to show you that you're going to get the same answer either way. So if I have 2.5 moles of copper, and I use all of it, right? So then I know that I make 2 moles of silver for every 1 mole of copper, which means that if I consume all of my copper, I'm going to make 5 moles of silver, right? And if I consume all of my silver nitrate, I know that I make 2 moles of silver for every 2 moles of silver nitrate. which means that I am going to make, right? 5.5 moles of silver if I use all of my silver nitrate. So, okay, let's taking a look at this. It's clear that 5 moles of silver is smaller than 5.5, which means that copper is my limiting reagent. Okay, cool, works. Now let's try it similar, but instead of converting it to moles of silver, let's convert it to moles of copper nitrate and just see if we get the same answer. So again, I'm going to start with 2.5 moles of copper, and I know that I make 1 mole of copper nitrate for every 1 mole of copper, which means that I'm going to make 2.5, I'll write it down here because I ran out of room, moles of copper nitrate. Okay. And then if I have I have 5.5 moles of silver nitrate, and I know that I get 1 mole of silver nitrate for every 2 moles of copper nitrate, I will make, if I consume all of my silver nitrate, I will make, 2.75 moles of copper nitrate. Okay, people. So I goofed here. Remember that these should be flipped. So this is going to be 1 mole of copper nitrate. And this is 1 mole of silver nitrate, 2 moles of silver nitrate down here. My ratio is correct. I just wrote the wrong substances next to it. Oops. Anyway, so looking at it this way, I still get here that my copper, because 2.5 is less than 2.75, my copper is still limiting. Okay, so it doesn't matter which product you pick. Convert them both into moles of product, one of the product, and whichever one is smaller is going to be your limiting reagent. Okay, so given that, if I know that copper is my limiting reagent, and I want to figure out how many moles of excess reagent are left over, we're continuing on to page 28 right now. Okay, so I'm going to use all of my copper. So because copper is limiting, it will all be consumed. So if it's all consumed, that means that the 2.5 moles of copper that I'm starting with will all be reacting. So I can figure out from there how many moles of the silver nitrate I'm going to use. So I know that I need 2 moles of silver nitrate for every 1 mole of copper. So what that means is that I'm going to consume 5 moles of silver nitrate. This is what I'm going to use. So this is what's consumed. Okay, so to figure out what's left over, what I have to do is I'm going to take what I used, or what I started with. I'm going to subtract off what I used, and then I'm going to get it, and that's going to be what's excess. In this case, I started with 5.5 moles of AgNO3. I consumed 5 moles of AgNO3. And then, so left over is 0.5 moles of AgNO3 in excess. So that's the amount that's left over after the reaction is complete. So when the reaction is complete, I'll have silver, I'll have copper nitrate, and I'll still have a little bit of silver nitrate left over. 0.5 moles of it exactly. Now, sometimes the question will ask you for the mass of the stuff that's left over. Sometimes the question will ask you to find the mass of product that's formed. And in that case, we'll have to do some unit converting, or maybe convert to grams, or, subtracting grams. It doesn't matter. There are a lot of different ways to solve these problems. The goal is make the units work, right? Just make them work. Make them work. For me, if I'm looking to find the amount of product that's formed, what I'll do is I'll get to so for example, if I'm looking for the mass of product, I'll just figure out the mass of product that's formed given both starting materials, and then circle the number that's smaller, because that's the one that's going to be the answer. And that also determines my limiting reagent without doing it in an extra step, unless that step is asked for. Does that make sense? Okay. We will do a lot more practice problems in class, but that's just to give you an idea. It's stoichiometry. It's just we got to figure out which reactant we're starting with. Same stuff, we just have an extra step at the beginning. Okay. One more kind of complication or addition to stoichiometry that we are going to do is dealing with this idea of a percent yield. So when we do our calculations for stoichiometry, what we're calculating is called a theoretical yield. And this is how much we could potentially isolate. This is how much we could, in theory, make, right? If all of our reaction went to product and we were able to perfectly isolate it, this is the amount of stuff that we could potentially isolate. Now, which is all well and good, but when I get in the lab, the reality is that chemistry is messy, and theoretical yields, I don't almost never actually get that amount of solid back or that amount of stuff because I lose some of it in the isolation product or some of it doesn't react, whatever. There's a lot of different reasons, but chemistry is messy. And so when we can look at something called the overall or the percent yield of a reaction, where we take the actual yield. This is the mass that you were able to isolate, or the amount isolated. And we divide it by the amount that we could have isolated, so the theoretical yield. And then we take that fraction and we multiply that by 100. That gives us our percent yield. Right? And in chemistry, anything over an 80% yield is really pretty darn good. Depending on the reaction, it could be higher, it could be lower. When I was doing chemistry, some reactions got a whopping 5% yield, and that's great. Depends on the reaction that you're looking at. So a couple of things about working with percent yield. You have to be given this number. You're not going to calculate that number. That's been given. This is the number that you calculate using stoichiometry. Okay, so let's take a look at what that potentially looks like by looking at the problem that's on page 29 in your packet. So we're looking at performing the reaction, mixing these together and looking at how much we can isolate. So solving for the percent yield. Okay. Let's think about this. So I know that I'm starting with this amount of iron phosphate and an excess of sodium sulfate. So my limiting reagent here is going to be the iron phosphate. Okay, so I'm going to start with iron phosphate. My goal is percent yield. So in order for me to find percent yield, I have to find the theoretical yield first. All right, how are we going to do that? So let's find our theoretical yield. This step here is looking at just stoichiometry, right? So I'm starting out with grams of iron 3 phosphate, and my goal unit over here is going to be grams of iron sulfate, so Fe2SO4 3, right? We can't get there in a single step, so we go from grams to moles of iron phosphate using the molar mass, and then we go to moles of iron sulfate using the mole ratio, and then we go to the molar mass of using the molar mass of that, we can go back to grams, just like a regular normal stoichiometry problem. And so when we set that up, using our dimensional analysis, FePO4, right, we convert that to moles. The molar mass of this turns out to be 150.82 grams of FePO4. Then I know based on my balanced equation that is up above that for every 1 mole of Fe2SO4 3, I need 2 moles of FePO4. And then the molar mass of iron 3 sulfate turns out to be 399.91 grams of Fe2SO4 3 for 1 mole E2SO4 3. And that turns out that if this reaction happens perfectly with significant figures, I can isolate 606 grams of Fe2SO4 3. Okay, cool, but not done yet. That's my theoretical yield. The question is asking me for the percent yield. So remember, the percent yield is equal to the actual yield over the theoretical times 100. So it's equal to 297 grams of Fe2SO4 3 over 606 grams of Fe2SO4 3, we'll multiply that by 100, and you should end up with a percent yield of 49.0%. So the yield of this reaction is just under 50%, which, it's not great, but it's not terrible either. Okay. So again, the same stoichiometry. There's just a little thing at the end to think about how much we could potentially make versus how much we actually make in a lab. So, question at the end of the video, on page 26, where the video notes are, I want you to try this question. This is incorporating everything we've talked about before and in this video. So we're mixing together 200 milliliters of a 0.15 molar solution of sodium phosphate and 250 milliliters of a 0.3 molar solution of silver nitrate, making a precipitate. I want to know the mass of the precipitate that you would expect to isolate. So how much could you make? How much precipitate could you make? And then you did the reaction, we're able to isolate that amount of solid. I want to know the percent yield of the reaction. Okay, give this a try. Remember, you have to try it for full credit for homework, and we'll talk about it in class tomorrow.